In this task, I'll use a digital elevation model to create several terrain-related datasets: slope, aspect, and hillshade. These elevation-derived datasets can be really useful in site selection analyses and other terrain-related spatial analyses. So here I've got QGIS Desktop open with a DEM, and this particular dataset covers the Sandia Mountains on the east side of Albuquerque, New Mexico. First, I'll investigate this layer. So I'm going to open up the layer properties for it. I'll go to the General tab, and I can see that it's in a UTM coordinate system, Zone 13, Nat 83, and UTM has XY coordinate values in meters. Next, I'll switch to the Metadata tab. I'm going to scroll down here, and I can see that it has a pixel size of 10 by 10, meaning each pixel represents 10 by 10 meters on the ground. Now I'll switch to the Style tab, and for me, the minimum and max values range from 1841 to 3094. And by default, the load min max value setting is cumulative count cut, and the accuracy is set to estimate. I'm going to switch this to min max and the accuracy to actual and click load. And now I'll get the actual range from min to max from 1775 to 3255. The elevation values of a DEM are typically either in feet or meters. The Sandia Mountain Range reaches an elevation of 10,678 feet above sea level. Therefore, I can deduce that these elevation units are in meters, not feet. Before working with DEMs, it's important to understand what the X, Y, and Z values are in. Here, all three are in meters. So now I'm going to use the Raster Terrain Analysis plugin to create the three elevation-related data sets. I'm going to close the layer properties. And I've already enabled the Raster Terrain Analysis plugin, and it's found on the Raster menu under Terrain Analysis. First, I'll create a hillshade image. I'll open the hillshade tool. And hillshades are really useful for creating nice maps of an area. They give you a sense of the terrain. So my elevation layer is going to be the DEM. I'm going to choose an output format, a Verdas Imagine image, and I'll click Browse and navigate to my Lab folder. And I'll name this hillshade.img. Click Save. I'm going to keep the defaults for the azimuth and the vertical angle of the sun. And the Z factor I'll keep as 1, 2. Since my X, Y, and Z units are all in meters, I can keep that at 1. If my X and Y units were in meters and my elevation were in feet, I'd have to put in a conversion factor from feet to meters. With those set, I'll click OK. And my hillshade is generated. So now that I've got a grayscale hillshade rendering, I'm going to use both the original DEM and the hillshade to create a color hillshade image. So I'm going to drag the hillshade below the DEM in the table of contents. And then I'll open the layer properties for the DEM and go to the Style tab. I'm going to change the render type to a single band pseudo color, change the color ramp to BRBG, and I'll change the load min max values to min max and accuracy to actual, and click Load, and finally click Classify. Now I'll go to the Transparency tab, and I'll use the Global Transparency slider and set it to about 50%. Then I'll click OK. And now I've got a nice color hillshade image looking at the hillshade through the semi-transparent colored DEM. Now I'll create a slope data set. I'll go to the Raster menu, to Terrain Analysis, Slope. The elevation layer is going to be the DEM. Make sure you don't set that to the hillshade. And I'll click the Browse button to browse. And I'll call this slope.img. Click Save. And click OK. This raster shows the steepest areas in white and the flattest terrain in black. And the tool determines the steepness of each pixel by comparing the elevation value of each individual pixel to that of the 8 surrounding pixels. The slope values are degrees of slope. And finally, I'll create an aspect data set. I'll go back to the Raster menu, Terrain Analysis, Aspect. Again, I'll use the DEM as the elevation layer. Click Browse. Save this as aspect.img. And click OK. Aspect measures which cardinal direction the terrain in each pixel is facing, north facing versus south facing, etc. The output values range from 0 to 360, representing degrees, where 0 equals north, 90 equals east, 180 degrees equals south, and 270 west. In the next task, you'll use some GRASS tools to reclassify raster data into meaningful categories.